All right. Hi, everyone. Is my screen visible?
Yeah, perfectly.
All right. So hello, I'm Atharv Sonwane. I'm a senior undergraduate student at BITS Pilani, and I'll be presenting our work on using program synthesis and inductive logic programming to solve Bongard problems. This is work with, as Cesar mentioned, Sharad, Tirtharaj, and Ashwin Srinivasan at AAIP, and in collaboration with Lovekesh and Gautam, Shroff at TCS Research. I'd just like to thank the organizers for giving us this opportunity to present this work in progress report. So in this work we tackle Bongard problems, which are a set of visual reasoning puzzles introduced by Mikhail Bongard in the 1960s. Each Bongard problem revolves around a certain abstract visual concept that has to be identified given some positive and negative examples. In this example, from the positive and the negative images, we can identify that the differentiating concept here is that the triangles are above the squares, above the circles in the positive examples. Such reasoning tasks can be particularly difficult since the abstract concepts involved can range widely and may require multiple steps of reasoning. In such reasoning tasks, we feel that deriving a useful representation of inputs is a key step to solving the problem. And for Bongard problems specifically, we feel that the representation of the input images needs to satisfy two objectives. First being that the representation should encapsulate relevant high-level concepts. So for example, in this Bongard problem, the concept is in the positive examples on the left, we have circles are present, while on the right, circles aren't present. So here, the representation we're using in the system should be able to encapsulate the idea of polygons and also the difference between polygons, such as squares, triangles, and circles. The second objective that we want the representation to satisfy is that it should allow for flexible abstraction formation on top of the relevant high-level concepts that we've identified. So for example, in this Bongard problem, the concept is that the enclosed figures have fewer sides than the enclosing figure. So even though our representation might have the high-level ideas of polygons and shapes, we need to do another step of reasoning to identify the fact that shapes can be enclosed amongst each other, and that is significant, and be able to compare between the number of sides. So in this work, we propose to use programs as intermediate representations of the input. More specifically, we use graphics programs, that is, programs that describe how to draw an image as the representation for the image. We propose a general framework that integrates this into a pipeline to solve Bongard problems. So the general framework consists of initially using a program synthesis module. In this way, using the Dreamcoder framework from Kevin Ellis et al., which I think was talked about in Armando's talk earlier. We use this to generate programs for each of the input images. These programs are then passed into a decoration module, which extracts additional information which might be relevant to identifying the concepts. And this additional information, along with the programs, are passed as background knowledge into the final stage, which is the theory generation, for which we use inductive logic programming. And the result is that we get a first-order logic statement, or a set of first-order logic clauses, which differentiate between the positive images and the negative images. The hypothesis, the idea behind using programs as representations of the input images, is that this allows for concept formation at various stages in the pipeline. Firstly, at the program synthesis stage, where Dreamcoder, through its abstraction step, invents new functions. For example, through Dreamcoder, we would be able to learn functions to draw polygons when it tries to draw multiple different polygons, and in the abstraction step identifies that having a function that does this is a useful function to have for the synthesis stage. So over there, we're generating the abstraction from the program synthesis stage itself. In the second stage, through extracting additional information from the programs in the decoration phase. And in the experiments we've done so far, we found that this is one of the most important parts, since where we extract additional information which allows for which would be relevant in the theory generation stage. And finally, the concepts that are incorporated into the representation in the first and second stage set the stage for learning further abstractions during the theory generation using ILP. So we can learn higher level theories which encapsulate concepts such as shapes being above or below each other, or smaller or larger than each other. This will be done at the final stage. So stage 1 of our system consists of using Dreamcoder to do program synthesis. So just a quick summary of a Dreamcoder is that it's a inductive program synthesis module which, given input-output examples, generates programs for those, and also learns a library of high-level functions or of functions on top of which it is found to be useful for during the synthesis stage. So Dreamcoder requires a set of basic primitives to be used as building blocks for generating the synthesized programs. Since in our case, we want to be able to synthesize programs that describe how to draw the input images, we want so basically we want programs that are instructions in how to control a pen on a canvas to draw the input image, similar to the logo programming language. So this is why the primitives we supply to the Dreamcoder consist of such building blocks such as an FW. So here you can see the FWRT primitive, which is just a function telling the cursor to move forward by a certain distance. We also include integers, control flow operations such as loop, and also rules that help or primitives that control how the pen is behaving, like pen up or pen down. These are basically primitives which are indicating how the pen should move on a canvas to draw the final image. And Dreamcoder is ingesting these and generating programs out of these. The images we pass to Dreamcoder are our own versions of the original Bongard problems. In our versions, the only difference being that we generate the images in such a way that it is easily usable by a Dreamcoder, and it's easy for Dreamcoder to generate programs for the images in the first place. However, we make sure to maintain the initial concept that was there in the Bongard problem in the first place. So here you can see that we have 12 images, 6 positive images and 6 negative images. Each and the concept for the Bongard problem here is that the triangles are above squares. This being an analogous problem that we've used to the original problem that I talked about, which had triangles above circles. So given these two things, we obtain from Dreamcoder a learned library. So for example, in this case, it learns a library containing 2 functions, a function for drawing triangles and another for drawing squares. And this can be understood since the input example images required us to draw basically triangles and shapes in different configurations. Along with this, Dreamcoder also outputs one solution program for each of the input images. The solution program it outputs would be the shortest length program it can find, given the search time that we've given it. So once we have the solution programs for the images, we move to the decoration phase, where we step through each program, one instruction at a time, while extracting state information at each step. In our implementation, we extract the position and coordinates of the cursor that's drawing the image. Since this is very relevant information that's included which is not directly available from the program text itself, but can be obtained by executing the program and looking at the internal program state. So in this way, we can construct a transition diagram. While at this point, we're using a very basic feature extractor, which is just stepping through and taking out the features that we want, we can envision using more complex methods and powerful methods based on deep learning that learn which features to extract in the first place that are relevant to the downstream task. This straight transition diagram is then converted into a first order logic sentence to be input into the theory generation stage with the following predicates: trace, which is used to associate a sequence of states with a program, and the has-info predicate, which is used to associate state information with the particular state, as well as the primitive that was called just before we got to the state. So The general idea being that we're encapsulating this whole state transition diagram we have into a first order logic sentence. For example, here you can see that this transition diagram is converted into this sentence with a single trace declaration and also has inflow declarations for each state. And we see that each of the primitives that were called in the program is also specified in that has inflow predicate declaration. These first order logic sentences for all of the input images are then passed as background knowledge to the ILP engine, which in our implementation is LF. We also include basic relation predicates such as greater than, less than, which are part of the background knowledge used to help aid in theory generation. The theory obtained from the ILP engine would be a set of first order logic clauses, which are satisfied by the background knowledge for the positive examples and not satisfied for the negative examples. So for our running example, the theory generated states that in the programs for the positive images, the triangle primitive must be called when the y coordinate is greater than the square, when the square primitive is called. So basically this is saying that the triangle should be above the square. Here you can see the importance of having the declaration phase where we extract additional state information from the program, since in the end the coordinate positions of the cursor were what allowed the ILP to find the differentiating theory. And while we use a first order logic representation coupled with ILP, this stage could also use other methods such as decision tree to generate the differentiating theory. So one important difference to note here is that by solving a Bongard problem, we mean generating a theory that solves the problem, that describes the difference between the negatives and the positives. So I think I'm going a little bit over time. I'll just take a couple more minutes and wrap the whole thing up quickly. So just a quick overview is that we generate programs for the input images from a Bongard problem. We decorate them by extracting additional information, and we generate a theory on top of those that differentiates between the positives and the negatives. I'll just go over a few results. Of the 14 Bongard problems that we evaluated on, our system is able to generate a theory for 8 of them. In this problem, the positive example consists of images with the same shape. The theory we generate says that the primitive, which is called in that there is a primitive which is called in 2 different states. So I'll just kind of point that out here. We have a has info. So you can see the third argument to the has info would be the primitive that we're calling, and we're saying that there are 2 different states in which we have the same primitive that's being called. Yeah, and this is basically saying that we're drawing the same shape twice in different ways. And that's encapsulating the concept, which was that we have similar shapes in the positive examples. On the example on the right, the concept is the presence of anti-clockwise spirals. The theory we generate states that the programs for the positive examples should contain either of 2 specific primitives. So here we're saying that we must have either F3 or F2. These specific F3 or F2 primitives were invented by Dreamcoder in the first stage of our system, and they are specific primitives which draw anti-clockwise spiral. So here we can see the importance of the abstractions generated by the Dreamcoder for theory generation, since it was able to identify these high-level idea of drawing anti-clockwise spirals, and this could then be directly used by the theory generator. So we have a few more results. Here we have number of shapes as the differentiating concepts. The theory just states that the program for the positive example should only contain 2 states. 2 states meaning that there would only be one primitive that is called, so only one shape that is drawn. On the second example, we have enclosed shapes having fewer sides, the one that I talked about earlier. This is a little bit more interesting one, since the theory that is learned is a little bit more complicated, saying that the smaller polygon has fewer sides than the larger polygon. Here we don't really, we're saying that a shape is enclosed if it's smaller, and also the way that we characterize the theory characterizes smaller polygons is by having the length of a smite smaller than the shape of the number of sides that are there in the polygon. which is a kind of indirect way of saying that the shape is small. So while we are able to generate theories successfully for some Bongard problems, we identify the main limitations of the approach that the approach currently has, and some directions for improvement. Among the limitations is our inability to represent complex visual features such as fill or complex curves. So you can see here the DL cell that we're using in the dream coder isn't really able to represent the fact that shapes can have fills or complex curves like in these Bongard problems. We also have issues with images that require long programs to describe them. So since the search in the program synthesis runs out of time before being able to find the required program. This occurs for images with large number of separate lines, as you can see in these examples. And finally, there may be cases that where while we may be able to generate a final theory successfully, this does not guarantee that the theory will encapsulate the required concept, since for example, you saw the example of the enclosed shape having fewer sides, where the theory is sort of suggesting what the concept was, but it's not directly. So yeah, I'll just wrap up with my final slide. Since we're running short on time. Looking forward, we see ways to improve the graphical program synthesis phase by using a learned metric for comparison rather than a pixel level comparison. So which makes the system really brittle currently. By using a learned metric, we can move to more natural inputs such as hand-drawn images. Using execution guided synthesis rather than enumeration, since we have access to the internal program state, which is really relevant to us. Also, the decoration phase can be improved by learning an automated feature extractor. So by using a learned feature extractor through deep learning, which can learn which features to extract, as opposed to the very basic one we're using currently. And in the final theory learning step, the construction, we can explore the construction of meta rules among programs of, so constructing meta rules from looking at theories generated for different Bongard problems and learning general concepts such as smallness, etc. And this can be done in final theory learning. So that concludes the presentation. I'd like to thank you all for listening. Sorry for taking up a little bit more time. And you can find the paper and the poster at these QR codes. And again, thank you for listening.